All right. So let's move on to our discussion. There's a question that I think you asked yesterday about, oh, sorry. About the possibility of when we were doing this, Bayesian concept learning, what if the data has errors in it, right? That I think there was a question like that last time, and the answer to that was that that is one of the good things about probabilistic methods is that they can accommodate error, because the fact is that any random variable can actually take any value just with certain probabilities, right? So even if you see a value that is very different from what you would expect, it is still possible. It's just with a low probability. So it is, these kind of methods are more forgiving to some of the errors that may be in the data, just because they model everything as a random variable, and by definition a random variable can take any values. Of course, if everything takes a very weird value, then the problem is not more of an error, but the fact that maybe the distribution that you're trying to fit, that assumption itself is wrong. So that's kind of that your inductive bias, your assumption, that inductive assumption itself is wrong, and then you might have to do something else. All right. So let's move on. So this is what we did last time, right? So last time what we did was that we had a set of hypotheses, 10 of them, and we wanted to figure out which hypothesis generated our data. All right. And of course, since this is a statistical method, so we don't want to pick one hypothesis. What we deal with are probability distributions over all of our hypotheses. So if you remember last time we did a experiment in which you, as a collective machine learning algorithm, first provided a prior. So prior is the belief on all of these hypotheses before you even see any data, right? So for example, in this particular experiment, if you remember, I said, I haven't shown you any data, and there are these 10 hypotheses. Tell me which one is most likely, right? So that is purely prior information. We don't know anything. So if all of you had, so I mean, this could have been a uniform sample, which means that if everyone had randomly picked one of the hypotheses because we didn't have any information, then this would have been pretty uniform. All these bars would have been of equal height. But what we saw was that some of them were higher than others. And the reason is that because you in your mind applied some prior information to that. So if you see, that's pretty interesting. So things like num1 to 100, that hypothesis got a lot of you chose that as a likely hypothesis. The reason being that that hypothesis would cover everything, right? So you are applying some prior onto that, right? So if I ask you, for example, that there is a place in the world, and I want you to predict the temperature of that place. Now, I don't tell you what place it is. I don't tell you what time of year it is. But because you know that temperatures are of fall within certain range, you will pick values there more than values which are really extreme, right? So that is sort of the prior information. However, after that, I showed you some data, right? I don't know if you can see that, but I showed you data which had 4 numbers, 16, 4, 64, 32, and then all of you actually revised your distribution. So collectively, this is the revised distribution over all the hypotheses, right? So two things. One is, of course, what you see is that some of the more likely ones got up, right? So that is one easy thing to observe, like power of 2, because all of these seem to be power of 2. Another interesting thing that we noted was that even though some of the hypotheses were still correct, for example, number 1 to 100, but a lot of you did not choose that because the likelihood of the data given this hypothesis would have been larger. So internally, you applied this notion of maximum likelihood estimation without really knowing that, right? Because you said that, and that in sort of simple English is known as the principle of least what was that? Was that the name? I don't know where it is, but it's basically you choose the one that arises the least suspicion. So for example, if you see 4 numbers, 16, 4, 64, 32, then, and if your hypothesis is 1 through 100, all numbers between 1 through 100, it raises a flag. Like it could be anything between 1 through 100. Why did you just see these 4 numbers, right? Whereas if your hypothesis is power of 2, then this raises less suspicion, right? So that is how we behave maybe in our heads. But statistically, what you did was you essentially chose the hypothesis which had the highest, which gave the highest likelihood to the data, right? So this is the notion of this Bayesian concept learning, that you start from a prior, right, and then you revise it after observing some data and get the posterior. Right? So posterior is so both of these are distributions over your hypotheses, right? But one of them you have seen the data and revised it. Okay. Then one thing we saw was, okay, how do we now use it? Once we have this posterior distribution, how we use it, and the way we can use it is, so what we want to do is, now if we get a new data point, let's say I get a new number 7, right? So we want to figure out what is the probability that that new number is also generated by that hypothesis, right? And then we looked at multiple options. One is that we could have chosen the hypothesis which gives the highest prior, maybe this one, right? We could have chosen the hypothesis that gave the highest likelihood, right? So here I don't show you likelihood, but the likelihood plot is somewhere here. I think this was a likelihood plot, and we could have chosen this one, and that's called the MLE estimate, maximum likelihood estimate. And the third thing is we could have chosen the one with the highest posterior, and that's called the maximum a posteriori estimate, or MAP estimate. All right. And then we looked at one more, which is in which we do not choose one hypothesis. We use all of them, and then we average it out based on their individual probabilities. And that is what we call Bayesian averaging. So a true Bayesian person would always go to Bayesian averaging. The idea is that we don't choose any one of them, right? And why do we do that? There's a reason for that, and there's a statistical reason for that we'll see later. But the idea behind Bayesian averaging is that, let's say you have a hypothesis posterior distribution which looks like this. Let's say you had only 4 hypotheses in your hypothesis space, and your posterior looks like this, right? So in this case, if you choose this as my most likely hypothesis, then it is fine, because this one is so far ahead of everybody else, right? But what if your posterior looks like this? So in this case, your MAP estimate would be H3, because this one is the highest. But what you see is that the others also have pretty significant probability of being the right hypothesis, right? So then it doesn't make sense to ignore all of these, right? So that is why what we do is we say, okay, what is the probability of this new data point to belong to whatever, to be generated by this hypothesis, given C is Hi, times probability of Hi given data, summation. Right, so this is what the Bayesian averaging would do. What the normal MAP estimate would do is it will just give you what is probability of y equal to c given c equal to h2, because h2 is the in this case is the MAP estimate. All right. So that is the difference. The reason we want sometimes to choose this kind of Bayesian averaging is so that we do not waste the wisdom of these other experts, right? Because they are also high. And then the good thing is that even if you apply this kind of logic to this, then because the probability of this is so high, it would still look very much like a MAP estimate, right? Because these ones will get downweighted because of their low probability. So it is still fine. So that's why we sort of look at Bayesian averaging a lot. Any questions so far? All right. All right, so okay, so now we are going to make it a little interesting. So this was about a set of hypotheses that we had and so on, right? But how do we use it in real life? So in real life, the way we will use it is, let's look at one example where we will try to estimate. We'll take one model, okay, one distribution, in this case Bernoulli distribution, and try to see how can we learn the parameters of that Bernoulli distribution. All right. Does anyone have a coin that I can borrow? Give it back. You just keep bills, huh? Anybody has a coin? Any coin? Coins are out of fashion. My last resort. Oh, there, got it. Oh, all right. Thank you very much. Thank you very much. I'll take all of your money later. But here, but let's say we have a coin here, right? It has two faces, heads, FDR, can you see it? And then the tail, right? So the idea is that we want to, let's say this coin is not fair. We don't know what is the probability of heads. In general, probability of heads is 1 or half. But in, let's say this is a weighted coin, we don't know what the probability of heads is, and we want to estimate, all right? And the way we will estimate is by tossing it a few times, right? So let's say we don't know anything about it. So we toss it a few times, let's say 4 tosses, tails, tails, heads, tails, right? So let's say this is our data set that we have observed by actually tossing this coin. Now we want to figure out what is the probability of heads, or we're going to call it theta. We're going to model it as a Bernoulli distribution, which means that there is a parameter theta, which is probability of heads, right? And why do we want to do that is because next, if I toss it, but I don't show it to you, right? So what will be this new, what is the probability that this new toss that I'm going to call X star is heads, right? Given the theta that we have, but we don't know this theta, right? So this is what we want to predict, or we want to compute. And this is kind of like machine learning, right? So we want to find what is the value for an unseen data point given this parameter. So first we want to learn this parameter using this training data. So that is the idea, all right? Any questions so far? So this is kind of like what we did in the class last time, is that we have bunch of hypotheses. Each value of theta is our hypothesis, and we want to figure out what is the best value. The only difference from last time is that instead of having 10 possible values, we have infinite values, right? So one thing, of course, we know is that theta is going to be between 0 and 1. But even in that range, you can have any theta, right? So theta could be 0.01, it could be 0.5, it could be 0.6, it could be 0.7, 0.75, anything. So the idea is, can we find what is the best theta that would have generated this data set, given that this is our training data, all right? So we want to do similar kind of thing. So we still want to get some kind of probability distribution over all possible values of theta, so that after that, we can either choose the highest value if we want to do MAP, or even if you look at the likelihoods, we can take the MLE estimate, or we can do Bayesian averaging. So that is the idea, right? So we want to figure out some distribution over all these thetas. So that is the main thing about statistical machine learning, if you look at it from a Bayesian setting, is that we treat our random variable, our parameter, the theta, also as a random variable, and we want to figure out what is the most likely value of this, given this is our D, all right? So let's look at it here. All right, so the first thing we can do is we can just do an MLE. Let's say we are not concerned about the prior at all, and all we want to do is an MLE estimate, or just an MLE of theta. So how do we do MLE? Is that we first compute the likelihood of our data, right? So our data, if you remember, is T, H, T, right? And we first compute the likelihood and then we maximize it. So that's the general idea. Right. So the first thing is, what is the likelihood? What is likelihood of D given the data is generated from a Bernoulli distribution, right, with parameter, with theta as a parameter, right? So we are assuming that that's our inductive bias, that our data is being generated by a Bernoulli distribution, but we don't know what the theta is, right? So now how do we compute the likelihood? So any point, so what is the probability of X to be tails, right, given theta is 1 minus theta, right? Because it's a Bernoulli distribution, the probability of observing a tails is just 1 minus theta. theta is the probability of observing the heads. So that means that so that will be the first one. Probability of observing tails again is 1 minus theta. Probability of observing heads is theta. Probability of observing tails is 1 minus theta, right? So now how do we compute likelihood? We just multiply these together, right? So the likelihood will be equal to 1 minus theta to the power 3 times theta, right? And the log likelihood is just the log of that. So that will be theta plus 3 log 1 minus theta. Oh, sorry, log theta. I just took the logs both sides, right? So this is the log likelihood, right? Any questions so far? So in general, if you had in your training data, let's say you had n examples, right? So let's say if training data had n tosses, right? So or n things here, and n1 were the number of heads, and n minus n1 were the number of tails, right? So then the likelihood of your data will be nothing but theta to the power n1 plus 1 times 1 minus theta to the power n minus n1, right? This is clear. There is no sort of the idea is that you toss the coin many times, n1 times you got a head, so the probability of those will be this, and n minus n1 times you got tail, so the total probability or the total likelihood will be this, right? Any questions so far? Right. So I'm going to also refer to this as P of D given theta, because that's the likelihood, right? Likelihood of my data set given theta is the parameter. So now the first thing, if you remember last time we saw, was how do we compute the maximum likelihood estimate. So we want to figure out the theta that gives me the best likelihood. Right now we are ignoring the prior. We just want to find the theta that gives me the highest value for this likelihood. And all you do then is you just say, let's compute the derivative of this with respect to theta, right? And we set it to 0 for highest likelihood, right? And then it just becomes some mathematical operations, right? So if I compute the derivative of this times, right, this becomes n1 theta n1 minus 1 times 1 minus theta n minus n1 minus right. I just did the chain rule, I suppose, right? So and then what we do is, so we can then sort of arrange it somehow. Let's see. So this becomes n1 theta n power minus 1 1 minus theta n minus n1 minus n minus n1 theta n to the power 1, sorry, n1 1 minus theta n minus n1 minus 1, and then you can pull out theta n1 minus n minus 1 1 minus theta n minus n1 minus 1 outside from all of this, and this will be left with n1 1 minus theta minus n minus n1 theta, right? Just rearranging stuff, right? And then we set this to 0. So we said that to get the highest value, we set this to 0. That means that we set this whole thing to 0. Now we assume that these things are not 0 by themselves. So this thing will go away. So that means that n1 1 minus theta minus n minus n1 theta is equal to 0, right? And then just collect all the theta terms on one side and other side, and then we get theta is equal to n1 over n. Right. And this is, we call it MLE estimate, because we maximize the likelihood to get it, right? So this is the value of theta that will give you the highest value. It will give you the highest likelihood for your given data, right? And if you think about it, this is simple, right? Even if we had not gone through this exercise, you could have done that yourself, that if you toss a coin 20 times and you see 18 heads, then you say probability of heads is 18 by 20, right? That's exactly what this does. So MLE is like the most sort of um, intuitive estimate for theta. All right, any questions so far? All right, so this is what MLE does, and we can stop here, right? If we do not believe in Bayesian statistics, then this is something that we could be happy with. That I got some data set which was here, and I computed the MLE here. So for example, for this data set, the MLE would be 1/4, and then when I want to find a new, so remember I tossed the coin and I hit it, right? So the probability of that new point to be heads given theta MLE would be just n1/n, right? So that's it. We could have stopped here, but of course we also want to talk about the prior as well, and there is a reason for doing that. And in fact, we can actually talk about the reason first. All right, so the reason for this is this notion of, right, why use a prior, right? And I'll tell you why to use a prior. But the reason for a prior is this notion of this black swan paradox. There's a book by Taleb called Black Swan, where they discuss this paradox. The idea is that, let's say you live in a place where you've always seen a white swan, right? If you're doing MLE estimate, since all you have seen is a white swan, it means that the probability of observing a black swan will be 0. Right? It's the same thing with this coin. If I had tossed it 3 times and I had only seen the tails, right, then by MLE estimate, the probability of heads would be 0, right? Because P according to MLE would be n1/n, and n1 is 0, right? But that is only because you looked at this data set. Maybe your data set is not enough, right? So you want to bring in some prior information to this so that those kind of degenerate issues don't occur. We don't give a 0 probability. Remember, in probability, you do not want to give a 0 probability, right? You do not want to be absolute. So that is where the prior helps, okay? So now we'll look at how to incorporate a prior. So the first thing, we'll look at this. So in the class notes, what I have done, just to keep it interesting, is that I've used n0 as the number of tails you get. In our derivation here, I use this as n minus n0. So it's the same thing, but you'll see a different notation here. All right. So now the next question is, how do we incorporate a prior? Now, what is a prior? A prior is a belief that you provide beforehand as to what will be the what will be the right answer. All right. So there are 2 ways to specify a prior. One is what we call a point prior, where you say, I think the prior probability, I think the value of theta is 0.5. Just one value, okay? That is what we call a point prior. But in probability, we don't like that kind of absolute values. We do not want to be absolute at all, right? So what we do instead is we use a different probability distribution to specify a prior, all right? So you can think of this, the prior, a prior on theta. Sounds like a novel name. So a prior on theta, what we want is, we want the theta prior to be between 0 and 1. That's a sort of a rule, right? And then we want to do things like this. So we do not want to specify priors like this, that okay, theta is 0.5, right? We want it to be more like a distribution. So maybe we can do it like this, that I want prior belief is that theta will be close to 0.5 with very high probability, and everywhere else it will be low, right? The reason we want to do this is because maybe we do not have a good sense of prior, right? Then we cannot specify a point prior, and then we want to specify a prior like this, that theta can be pretty much anything between 0 and 1. This is what we call not a very useful prior, right? This is but in general we want to be able to specify different types of prior. So this would be where we say that I don't know what theta is, but prior information tells me that theta will be towards 0 more than towards 1. So this is a different way we can specify prior. Now, how do we mathematically specify this prior is by using a different distribution on theta, all right? And here is where I introduce a new distribution called beta distribution. So a beta distribution is a distribution like Gaussian or anything else that you might have seen, The only thing is that its PDF is slightly different. Okay. Now theta is a continuous value. That means that the distribution on theta will also be a continuous distribution, right? Because theta can take any value between 0 and 1. So the distribution over theta, the prior distribution that we will use here is beta distribution. All right. You can choose any other distribution if you want. If you have any other distribution which lets you sample things between 0 and 1, you can use that as well. Here we use beta, and I'll tell you why. It gives you some interesting properties later on. All right. So let's first quickly look at beta distribution itself. So beta distribution gives out a sample between 0 and 1. We call that theta. It has two parameters. We call those hyperparameters because those are things that we need to specify, A and B. And the PDF is specified like this. 1 over B A comma B, theta A minus 1, 1 minus theta B minus 1, which means that the probability at any theta will be given by this, or the density at any theta will be given by this. All right. So this denominator over here is what we call the beta function, and that is computed using this gamma function. So this is, once you have A and B, this is pretty much a constant, right? We don't really worry about it. But if you go to Python, you can compute it. Gamma function is nothing but like an extension of factorial to real numbers, right? So you know what a factorial is. Factorial of 4 is 4, multiply everything together. For gamma function, now if instead of 4 we have a like 3.7, then how do you compute the factorial? So the analog of factorial in this continuous space is what we call a gamma function, which has this formula. But for this whole exercise that we are going to do, you can ignore all of this. All right, you can ignore all of this. The main thing we want to remember is that the beta distribution's form is some constant times theta A minus 1, 1 minus theta B minus 1. And by changing this A and B, we can change the form of this function. So if you go to our, the list of all of our notebooks that I have, go to beta distribution demo, and this is where I have used the SciPy beta distribution. So this is what it does. This is the beta distribution's PDF, and this is so remember, every time the PDF will only be defined between 0 and 1, because beta distribution, the probability of anything outside 0 and 1 will always be 0. But inside, you can control the shape by changing A and B, right? So here A was 0.1 and B was 0.1. So you can think of this as a prior, where you say that I think that the theta for this coin will either be very high or very low, right? But you can change it. Instead of that, you can say 2 and 1, and then it will look like this, right? So the probability is almost changing linearly. You can make it 2, 2, then it will look like this. It says the probability is between 0 and 1, more concentrated around 0.5, and then slowly around here. You can make it even sharper if you don't like this. Say 0.2. Oh, sorry, not this. And then it becomes more sharper, right? You can make 10. It becomes sharper, right? So the idea is that by changing your A and B, you can change your prior. You can make your prior focused on certain value. You can make it asymmetric, and then it goes this way, and so on, right? So you can play with it and you can change, right? So given your A and B, you have specified a prior. That is the idea, all right? So let's see how we use it. So of course, one thing you can do is you can ignore all of your training data and just use the maximum a priori estimate of theta using this plot, right? For example, let's say for the value of you can say, hey, at theta 0.5 is the highest value that I'm getting. So let's use that as my theta for this coin. So that's called a priori or a prior estimate. But that's not a very good estimate because you're not using any training data at all. So that's sort of a silly one. Okay, but now what we want to do is, now we want to combine the prior with the likelihood. Remember, the likelihood was here. This is the likelihood estimate, right? And this is the prior. And now we want to combine it to get the posterior. right? That's what we did on our example last time as well. And you know how to combine prior and posterior. It's just by using Bayes' rule. Any questions so far? I don't think I'll need this more. Thank you very much. All right, so we're going to do how to do prior, posterior from prior, right? So remember that the posterior, so we want to compute the posterior on theta. So what are we computing the posterior of? We are computing the posterior distribution of theta after we have observed our training data, all right? And this, if you remember, is nothing but probability, the likelihood of data given theta times the prior distribution over theta, right, divided by just all the summations, right, that denominator. Now in this case, remember that theta is no longer a discrete value. That means you can't have a summation here. So here instead we will put an integral, and this will be p d theta prime. So for all values of theta prime, d theta prime, right, 0 to 1. So this is the posterior distribution, all right? And this you will see if you do a lot of machine learning, you will come across this more and more. This is not just focused on beta distribution or a coin tossing. Anytime you want to compute the posterior distribution of your parameters, whatever your parameters of your model are, given your data, you have to apply this, right? So the question is, what are each one of these values? So the first thing I want you to understand is that this part is not very useful, all right, because this will be constant for all theta, and eventually we want to use the best theta anyway, right? So we can actually ignore this, and we will say that my p theta given d is proportional to p d given theta times p theta. Now remember, what is p d given theta, right? P d given theta is nothing but theta to the power n 1 minus theta n minus n1, right? That is the number of heads we saw and number of tails we saw, times what is p theta, right? Remember, this is a beta distribution, which means that the probability distribution for this is theta to the power a minus 1 minus theta to the power b minus 1, right? Now if you multiply all of these, you get theta n1 plus a minus 1 minus theta n plus b minus n1 minus 1. So this is the posterior distribution, all right? And what you see immediately is that this posterior distribution has the same form, or the PDF of this posterior distribution has the same form as the prior, right? It has theta, so the probability density at theta is given by theta raised to something, and 1 minus theta raised to something else, right? So that is the idea, which means that the posterior is also a beta distribution. You can actually compute all of this and you can get the exact value. So the idea is that you started with a beta prior, right? And then you multiplied it with our likelihood, and the posterior distribution that you got was also a beta distribution. So this is what we call, and this happened because beta and Bernoulli, they share a special relationship. So the likelihood was computed using a Bernoulli distribution, right? And the prior was beta. And the reason that after we multiplied this, the prior with likelihood, we got a posterior which is the same as the prior, is because beta and Bernoulli are what we call conjugate priors. So they are friends, and they have this relationship that beta distribution is the conjugate prior of Bernoulli, and because of that, the posterior has the same form as prior. Okay, and the reason this is good is because now we can work with this distribution very easily. See, if they were not conjugate, then the form of this would have been anything, and it might have been very hard to compute mathematically, right? But here, because of this nice property, things haven't changed that much. You started with a prior distribution, so think of it this way, that you would have you would have started with this, right? This is a prior distribution on theta, prior beta distribution, and then you multiplied that likelihood, and all that would have happened is that this would have changed a little bit. All right. So, for example, let's say our prior distribution was this. All I mean, what we are saying is that that theta would be 0.5, right? It's our prior belief is that this is a fair coin, but then we saw a data set in which we see only tails, right? All tails. What would happen is that when you multiply that prior with the likelihood, this would shift. This would shift left, because now your theta can be because based on the training data, we think that theta is lower, right? Because the probability of tails is very high. So this will shift a little bit. But it avoids this notion of this issue of the black swan paradox, because it would not make it 0, right? So this prior is controlling some prior belief, and then the likelihood is telling you something, and this posterior is just sort of an aggregation of the two. All right. Any questions so far? All right. So that is the idea, right? So the posterior also is a beta distribution with these as the parameters. All right. So it's a new beta distribution. Remember, your theta was a prior distribution on theta was a beta distribution with a comma b, right? And now your posterior distribution looks like this. All right. So that is the sort of the beauty of these conjugate priors, is that the posterior is same as the prior. All right. Then we can, of course, this is a distribution, so we can compute the expectation, right? So expectation of any beta distribution is written as this. So that means our prior p theta was a beta distribution given a comma b, which means that the expected value of theta, which is nothing but you just take a integral over all possible values multiplied by p theta, right? That is given by a over a plus b. I will not derive this, but this is sort of, let's keep it as a result that we know. All right. Now the posterior, we said, is also a beta distribution, but it is beta theta times n1 plus a, comma n0. I apologize, but I'm going to use n0, but this is easy to use. But n0 is nothing but n minus n1, the number of tails you got, right? So which means that the expectation of this new random variable theta given d is going to be n1 plus a over n1 plus n0 plus a plus b. All right. So that is the idea. So you can compute the expected value as well. Okay. But now we want to use it to predict our x, right? Remember, now I have a new coin. I don't know what it is, heads or tails, and I want to figure out what is the probability of heads, right? So how do we use this? That's easy again. We can either take the MAP estimate, which means that we can take the value that maximizes the posterior, and that will be our MAP estimate. And in case of beta distribution, you can actually compute it when you go home. I think I have the notes in the class. If you maximize it with respect to theta, you will see that the MAP estimate looks like this: a plus n1 minus 1 over a plus b plus n minus 2. All right. So the idea is that the theta, so remember, the MLE for this exercise was that theta MLE is nothing but n1 over n1 plus n0, right? Number of heads that you saw out of a total, right? The map is actually, if you maximize that probability, it will come out to a plus n1 minus 1 over a plus b plus n1 plus n0 minus 2. So all that is happening is that if you had not used the prior, then you would have used this as your estimate. But by using the prior, you're adding these prior information into it. So it kind of, so even if you had not seen any heads at all, right? So even if your heads was 0, you would still see some probability because A would have controlled that, right? So that is the idea. So this is the MAP estimate This is the MLE. Of course, we could have used the prior estimate as well, but that doesn't make much sense, right? Any questions so far? The last thing I want to talk about is the Bayesian averaging approach, right? So in Bayesian averaging, we do not use one value out of that distribution. So let's say our MAP estimate looks like this. This is over theta, right? And this is, let's say, 0.5, 0, and 1. And this is what, by multiplying our prior and posterior, this is our thing that we use. So the MAP estimate would be this one, the one that is giving the highest value, right? But let's say we do not want to just take one value, we want to average it over all of this, right? So what we would do is that in Bayesian averaging, we will do that averaging, right? So just before that, so the probability of a new data point to be heads here will be just theta MLE, which is this. The probability of new data point to be heads here would just be theta MAP. But in Bayesian averaging, things change. So the probability of new data point to be heads will not be any one value. It will be, we will take every possible value. So the probability of X to be heads given any theta times probability of theta given D, that's a posterior, over all possible values of theta. Because we are going to use each one of, we are going to consider each value of theta as a possible expert. And then we are going to check the answer that each one of them is giving, but we are going to multiply it by their probabilities, right? So if you calculate this is also easy to calculate, simply because this is all this posterior thing. So this is the probability of observing heads given any theta is theta, right? And this is P theta given D times D theta, right? Now this is nothing but the expectation, right? This is the expression for the expectation of theta, which means that this, I wrote it earlier somewhere, expected value of this is n1 plus a over n1 plus n0 plus a plus b. All right, so this is the value that you will get. The probability of a new data point to be heads is this if you use the Bayesian averaging. So you can compare the three possible answers. So MLE will say that the probability of new heads is this. It will just count the number of heads you saw. MAP will say that the probability is this expression, and Bayesian averaging will say it is this. So they are slightly different answers. All right. Any questions so far? Cool. All right. So this is sort of the whole exercise that I suggest that when you go back, you try it too. And then this is what I talked earlier, right? This notion of black swan paradox is that if your D had just tails, right, then your N1 was 0, of course, then your theta hat MLE would be 0. But that's just because you're just overfitting on your theta, right? So this is also, you can think of it as a way of avoiding overfitting. A way of avoiding just following the training data is by also incorporating the prior, because the prior kind of tells you, okay, this is what it is before seeing any data. And the Bayesian approach sort of, Bayesian and even MAP, both of them will help you avoid that 0 probability, all right? Then the next question is why do we use this Bayesian averaging and not just MAP? And I showed you a reason, right? I showed you a reason that, you know, if your posterior is peaked at one point, then it is okay to use MAP because that value is very probable. But if your posterior is very smooth, which means that many values of theta could be possible with nearly similar probabilities, then you want to do Bayesian averaging because then you are not throwing away any useful information, right? In fact, in statistics, there is a statistical reason for that. The statistical reason is that if you compute the variance of theta, now remember, theta is a random variable, right? So you can compute the variance. Variance is how much it sort of varies across the mean, right? And what you will see is that if you use MAP, the variance can become very high, which means that even though you might use just one value of theta, right, because the variance of theta is so high, then you might get incorrect results because it's not okay to use one value of theta when your theta is varying so much, right? And that's why we use Bayesian averaging. I mean, this is sort of a statistical reason to do that. All right. The next thing what we will do is we will do the same exercise for a different distribution. All right. So far we did this exercise for a Bernoulli distribution. We had a coin, and we were trying to figure out what is the theta given we saw a few tosses, right? And then we saw ways to do that. Now we're going to change it a little bit and say, instead of a coin, what you observe is not just a toss of a coin, but an actual value. All right. In fact, we will see that x is a vector of values. All right. And now, how can we compute the parameters of the distribution that generated these values, assuming that these values were generated by a multivariate Gaussian? So in the class in 2 weeks back, I showed you the expression for a multivariate Gaussian. So this is the PDF, right? Reason you see a fancy n is that we treat Gaussian in a slightly special way. So this is basically another symbol for a Gaussian distribution, and this is the PDF or the density at x for this distribution, and it is given using this expression. All right. So this is the PDF. We want now, if I give you some x's, how can you compute sigma and mu? That is sort of the problem, right? And it is the same problem of concept learning, except that instead of Bernoulli, we have a slightly different distribution. Let's get started, and then we can. So the idea is that you have some x's given to you, right? And let's say x is in some d-dimensional space. That means that x, so assume d is 3, right? So you have bunch of x's given to you, 0.7, 0.2, 0.1, 0.6, 0.4, minus 0.2, 3.1, 2.7, minus 9.8, and so on. So this is your training data that you're given, and now, and you're assuming that x is generated by a multivariate normal distribution, which means that implies that the probability of x, or the density, because x is going to be continuous, right, at any value is a function of mu and sigma, and it is given by 1 over 2 pi to the power d by 2, let's use small d by 2, and then the determinant of this covariance matrix and exp. So this is a standard sort of the form of this function, right? Now what we want to do, right? So you can compute the PDF of x if you knew sigma and mu. But now we want to do the other way, right? We don't know what sigma and mu is. All we have done is we have made an inductive hypothesis that x is generated by this type of distribution. Now, given this data, how can we estimate mu and sigma, right? So this is the question, and the strategy is still the same. We'll first compute the likelihood of our data set given this distribution. We'll maximize it to get the MLE estimate for mu and sigma. Then we will put some priors on mu and sigma. Now remember, things have changed here a little bit, that instead of one parameter theta, now we have two parameters, mu and sigma, right? So we have to estimate, we have to put priors on mu and sigma. We'll compute a posterior on mu and sigma with that, and then go on like that, right? So that is the idea. So in next class, what we will do is we will see how to compute mu MLE and sigma MLE, and then then probability of mu given data, which will be like our posterior, and probability distribution of sigma given data, and then also the map. By maximizing this, we can get the map and sigma map, right? But the things have become a little more interesting here. The reason is that now your mu is not a number, right? If you look at this, right, x is a vector, mu is also a vector. Mu is also in this d-dimensional space, right? It's a vector, and sigma actually is a matrix. Sigma is going to be a d cross d matrix because it's a covariance matrix, right? So how do we estimate that, and how do we put priors on matrices and vectors, and how do we put conjugate priors so that we don't get lost into all the mathematics? Those are the things that we will see in the next class. All right, any questions so far? Okay, all right, so let's meet on Monday. So I had one announcement. This is for 474 section. Next Friday is our midterm. That means that Friday morning we will not have the recitation. The midterm is from 8 to 10. We still have 2 recitations on Monday at 10 and 3, and the TA is going to sort of do a review for the midterm, so it will be useful. So if there are students who are not able to make it to any of the Monday recitations, the TA is going to record it and put it online so that you can see it. But if you still want to go through the stuff, set up a time with the TAs and they can sort of help you out. All right. Okay. Thank you very much.